previous class we have discussed about this matrix representations of relations, and we have the how to represent the union and intersection of these relations, or how we represent the powers of the relations. Okay, and this is the power of the relation. That means Rn is what? Rn is equal to R composite Rn plus 1. This is very important. Okay, and we may write it like this. Suppose we have to find the R square, then we have the R composite R, and in matrix notations we are writing like this: Mr square. This is equal to Mr. We are writing like this too. Okay, and what is this? This is the Boolean product of this. This is the Boolean product of this M and Mr and Mr. Like now today one more thing, so we just skip in the previous class, that is the inverse of the relations. Today we'll discuss this one, the inverse of the relations, because in later case we required this inverse of a inverse of relation. So I'm considering a single set, A, B non-empty set, okay, and R is defined by AB, such that AB belongs to A. So it is the relation. So how can you define this one, R inverse? So R inverse is defined like, that means if R is related to B, okay, so this is R, then R inverse is equal, this is R inverse is denoted by BA, okay, and so that this AB belongs to R and AB belongs to this A. Okay, so what is the inverse of the relations? Okay, that means suppose if we have a equal to 1, 2, 3, okay, and if you define the relations like 1, 1, 2, 3, and 2, 1, okay, then R inverse will be how much? Sorry, R inverse will be consist of, if AB belongs to R, then BA must belong to R inverse. So here we have 1, 1. It is 2, 3, so 3, 2 should be here, and this is 1, 2, so 1, 2 should be here. This is your R inverse. Is it clear? क्या clear हुआ?
Yes, sir.
Hello. Okay. Now, if it is clear, then solve one problem. This is and this is a simple definition of the inverse of the relations. Question is, if let R be a relation on any non-empty set A, okay, then prove that. First one is if R is reflexive, So is R inverse is also reflexive. Second, R, it is obvious. R is symmetric if and only if R is equal to R inverse, and third is equal to R is anti-symmetric if this is also if R intersection R this is equal to identity. IA it is written. What is the meaning of IA? IA means that means the relation. It is simply a relation that contains all the elements, like here I am defined the IA is the relation AA, and A belongs to this. This is your IA. Okay. So now just try to prove this one. Okay. And tell me the logic. Try to prove this one.
Do we have to prove using the example?
Consider any, suppose you consider any, not example. Suppose you are taking any set. Suppose AB. Suppose A reflexive. First one is I am going to solve. First one is AA. This belongs to R. If it is, suppose if R is reflexive, then AA belongs to R. Okay, and this is valid for all A. Okay, so if AA belongs to R, then from the definition of R inverse, this A is this and this A is this. Belongs to R inverse, and it is also valid for all. Therefore, inverse of R is reflexive. Is it clear? In this way, second and third also. Try to solve it. After that, we will start the diagram. Second one is also simple. Suppose R is symmetric. So therefore AB belongs to R. All AB are the elements of A. This implies, sorry, BA belongs to R, and this implies AB belongs to R inverse. So AB belongs to R implies AB belongs to R inverse. So therefore, we may write, and if AB belongs to R, and if it is symmetric, then definitely BA also belongs to R. Okay, and if BA belongs to R, then AB also belongs to R inverse. So R is equal to R inverse. So if it is symmetric, then this condition holds. Transitive, anti-symmetric. Anti-symmetric, how you prove this one? Anti-symmetric means yes. Okay. Suppose AB belongs to R. AB belongs to R. Okay. And How you prove this? Intersection of this is equal to IA. If R is anti-symmetric, that means if these and from the basic definitions and BA belongs to R, then A and B must be equal. Okay, and in that case we can say that R is anti-symmetric. So suppose you should write here, let R be anti-symmetric. Anti-symmetric. Then AB belongs to R, and this is R implies AB belongs to R and this is BA, so AB belongs to R inverse, and this implies AB belongs to R intersection R inverse. So what is AB belongs to this, and what it says that anti-symmetric if this is equal to this, that means how you say, if R is anti-symmetric, no, this is the second part. We don't write this one. You should write a letter R intersection R inverse is equal to IA, like this. So now two conditions: AB belongs to R intersection R inverse, and this is equal to, the since you may write it, since R intersection R inverse. This is the one part. We have the two parts, if and only if parts. I am writing the only if part. This is subset of sorry, it should write here subset of, not equal to. It is a subset of. Just make it correct. Make the correction. Subset of this. We should not write these two sets are equals. So this is equal to IA, and therefore we may write it A is equal to B. Since this is the subset of this and AB belongs to this, that means, and IA means what? This contains the elements like AA or BB like this, and this is the subset of IA, and this element belongs to this. That means definitely A is equal to B, otherwise it will not a subset of IA. So this is the condition for the anti-symmetry. Okay. So these are the some examples, and you can see the other examples from the book also. Now, come to today's topic, that is the matrix representation with matrix representation in directed graph, or you may write it as a digraph, or it is also called directed graph. Okay. Sorry, what I'm writing. Representation of relation. using digraph. So this is the heading. Oh, okay. Graph. Directed graph, it is a very simple. There are two way. One is the matrix and second is the graph. There are the two way to represent the relations. Okay. Now, sometimes it is useful to use the matrix and sometimes it is useful to use the graph. So basically, when we design something, we first draw the graph, and from that graph, we convert it to the matrix forms, and then we go for some computational work. Okay, so first come to the diagram. So what is the diagram? Okay, so diagram consists of, I'm simply write down the definitions. So in diagrams, it is actually pictorial representation of the uh, relations. So what is the directed graph? Directed graph is uh, you may write the diagram. Diagram consists of points. Okay, consist of points instead of points. I also write the vertex. Consist of vertex. Okay, and the set of vertex is said to be V. It is generally denoted by V. Uh, set of vertex is denoted by V. This consists of the vertex, or sometimes it is also said to be the nodes basically. Okay, diagram of vertex and edges, edges, and the set of edges is denoted by E. By V. And the edges. Okay, edges and the edges. This the diagram consists of the vertex and the edges. Okay, so not write the definition here. What is the edges? The edges are the ordered pair. Ordered pair of vertex or the vertices. Okay. So what is the diagram consists of the vertex and edges. And what is the edges? Edges are the ordered pair. This is important. This is the ordered pair of the vertex. So you see, like suppose we have points on the relation. Suppose the points, suppose this is A1, A2, A3, A4. These are the elements of some set A. Okay, and then you construct the pair. That's one. Okay, and these are the vertex. These are the vertices, and you construct the pair of vertices. That means A1, A2, or suppose A1, A1, A3, or suppose A2, A3. Okay, these are the edges. So question is, how can you define a ordered relation using this? Okay, come to an example. Suppose we have a suppose A is equal to ABCD. Suppose, okay, and suppose we consider the relations R. R is equal to suppose AA, BB, okay, and AD, okay, CD, DC, okay. Then suppose AC is there. I'm considering this. Okay. Now draw the diagram. Uh, if you want to draw the matrix, then what you will do? Matrix. Then what you will do? Uh, okay. So here we have a ABCD, and here we have a ABCD. Now A is here. We said 1. Can anyone tell me what are the rows of this? Hello. Can anybody tell
Yes,
me
sir.
what is? Yeah. What are the rows? What are the rows of this matrix?
0, 1,
Mm-hmm.
1 0
One.
1 0 1
Okay.
0 1.
So you say, well, AA, B is here. Okay. First you write down 1 over here, everywhere. AD. So A D. A D. First is A. This is row. This is column. First D, and then CD. C D. DC. D C, and AC. A C. So rest are 0. So this is the matrix representative. If you want to use this diagram, so first what do you, so we first write down the nodes, okay, like this. Any way you can write it, not in these 4 corners. And these are the A, this is B, and this is C, and this is D, suppose. First you come to AA. AA is there, so we have anti-clockwise rotation of this. This represent A is R related to A. This is the notation. A is R related to A, anti-clockwise rotations. Then B is R related to B. B is R related to B. A is related to D. This is the D. So it is like this. And you can write it like this. That means A is directed towards B. So that's why it is named the directed graph. Directed means we must have some directions. Okay. This represents A to D, not from D to A. Similarly, C to D. C to D, but this direction. C to D. D to C. D to C, that means this. Sorry. D to C, and A to C. A to C. Okay. So this is the directed graph. If you add 2 more, A to B, and B to C, then A to V, you simply add this on A to V, and this is B to C. This is the directed graph. Okay, and there are lots of application of this directed graph also. Is it clear how to write down this one?
Yes, sir.
Yes, sir.
Now you see here, from this graph, from this matrix, you see, if you are one more thing, if you are using this matrix, from here easily you can characterize the relations, because you see, if the diagonal elements are 1, all the diagonal elements are 1, then it is reflexive. Okay, if each core node has loop, then it is reflexive, not symmetric. If each elements of the diagonals are 1, then it is reflexive. In case of the matrix repainting, in diagram, A is related to R, that means there is a loop over A. There is a loop in B, and we haven't any loop at the node C and D. That means it is not reflexive. That means C is not related to C and D is not related to D. Okay. Now, is it symmetric? First thing. So, reflexive, what is the conditions? Reflexive, if each node has loop. If each node has loop, then we say that it is reflexive. Is it? Is it symmetric? From this graph, tell me whether it is symmetric. Is it? No.
No, sir.
No. So you see here only one more limit is there. Okay. So why it is not symmetric? You see here, if C is related to D and then D is related to C. But what about this AC? A is related to C, but C is not related to A. Okay. C is not related to A. So you can write it. One thing is, first one is, it is reflexive for the diagram if every vertex has not if there is a loop at every vertex, first one is. Second, symmetric. What is this edge? First, I am just telling you what are the edges. This you see here, these are the edges. These are the edges. That means this is the point AC. A to C directed graph, it is AC. So it is the edge. Okay. Okay. So when you say that it is symmetric, relations, symmetric, just tell me what is the
When AC
symmetric?
and CA both belong.
So you see symmetric, you can write this if each edge, that means AC, this is the edge. Okay, each edge, each edge or every, better to write the every. Okay, every edge has opposite edge. Okay, that means if AC is the edge, then definitely we must have CA. There must consist CA as the edge in this diagram also. Otherwise, it is not the symmetric. And when we say that anti-symmetric, if it is anti-symmetric, if no two edges are in the opposite direction, Okay, so what is the definition of anti-symmetric? If A is related to B and V is related to A, then this must be or implied by A is equal to V. That means if no edges exist, opposite edges exist, then it is the antisymmetric case. It is more easy to identify. If A to B, if it, you see here, it is not antisymmetric. If you discard this one, okay, D to C, then this becomes the antisymmetric. So if there is a edge from A to B and B to A, then A is equal to B. Based on this, we can say that a relation is antisymmetric if we haven't any two edges in the opposite direction between the distinct vertices, not the same. We haven't any opposite edge or opposite opposite edge for the two distinct nodes of the digraph. Here we have it, so it is not a antisymmetric, not symmetric. Okay, now I am just giving you a question. Question is one is draw the digraph of, suppose we have a like this, the 1 0 0 1 0 0. This is MR. Okay, and second, find the matrix, find MR, where from the diagram so just I am not defining the node. You can define 1 2 3 ABCD, whatever maybe. Okay,
Okay.
so solve these two. Solve these two. Can anybody present this? And by the way, I am drawing this
Yes, yes,
diagram.
solving.
Okay, solve it. So we have how many? 4 nodes are there. So first one solution. 4 nodes, draw your 4 nodes. Okay. So from this matrix, we see that the diagonal elements are 1. So all node sets
Blue.
and suppose give the name A, B, this is C, and this is D. Okay. So A, B, C, D. Suppose now all the entries are 1. That means it is reflexive. Next, this is the position of A, B. A to B. We have A to B, but we haven't B to A. You see, it is not symmetric. Okay. So we have from A to B directions. Then we have A to C, but not C to A. So A to C. Like this. Then we haven't any A to D. Then we have a B to B and nowhere. Then we have a C to C and C to D. C to D. So C to D. We have a graph like this. And then D to A, D to A, and D to D, D to D. So this is the basic diagram.
Yes, sir. So in
Is it
question
clear?
number 2,
Yeah, question number
you
2.
put
Give
same
the name
directional arrow, sir, in
A,
first line.
B. Oi,
It
sorry.
the arrow.
Okay, change it.
Yes, sir. Done.
Okay, so write down the matrix 2.
Sir, is it 1 1 1 1 1 1 1 0?
No. 1 1 0. You see 1 1 1 1. It is 0.
Yes, sir.
There hasn't any loop in the C. Okay. Now we have a to B as well as B to A also. You see here, it is a not reflexive, but it is a symmetric because each edge has opposite edge. Each edge has opposite edge.
Yes, sir.
Okay. So A to B, we have A to B, similarly B to A also. And we have A to C and we have a C to A also. Okay. But B to C, we haven't any B to, yeah. B to C and C to B, it has also. So you see here, it is symmetric. You see this one and this one and this one, but it is not reflexive. If we give a loop at the node C, then this becomes the symmetric or reflexive also. Okay, is it transitive? If it is 1 1, then it is transitive because we have a to B, then B to A, then we have A to C also. It is transitive also. Is it clear?
Yes, sir.
Okay. Now come to the very important thing, closure. Actually, now we need to using the matrix or using the or the construction of the transitive relation especially, it is not so easy. Okay, but we have a algorithm using that we can find the transitive closure. That means any set is given, any relation defined over any set is given, but that relation is does not hold the transitivity or symmetricity or the reflexive property, but we can make that relations reflexive or anti-symmetric, symmetric, transitive by adding some new elements, and that defines our from there we came to a new concept, that is the closure of our relations. I'm just brief this one. Okay, closure of relations. Closure of relations, that means suppose we have a non-empty set and it is a non-empty set. Very important part it is. non-empty set. And P, what is the P? Is any property. Any property of relation. So what are that properties? First one is it may be reflexive, it may be symmetric, anti-symmetric, transitive. So basically we are considering these three. Now R is any relation. Now these relations may or may not contains any of these properties. May or may not. Okay, clear. Definition is not so important. Understanding is very important. So relation is, this relation may or may not contains any property. Suppose we consider that these relations will not contains the reflexive property. Okay. Now suppose in a set A 1 2 3 1 2 3 R is defined like 1 1 2 2 1 2 2 1 like this. Okay. Is it reflexive? Is it reflexive? Hello?
Yes, sir.
Is it reflexive?
No, sir. No, sir. 3 is not there.
No, sir.
Where are the other students? How many students are there? Out of 65, no one are giving answer. By the way, it is not a reflexive.
Reflexive.
Okay. How can you make it reflexive? We define a set S. Okay,
I
such that this is 2 2. And what is the least entry we should involve here or include here so that this becomes the reflexive? So it is a
3,
3
sir.
3.
3.
And this S must contains R also. That means this 2 belongs to R. We have a 1 2 over here and 2 1 is over. So this is S. We may consider the another, suppose S1, such that 1 1 2 2 3 3 1 2 2 1 3 2 like this. We can consider. Okay. Now, can you see that S is the subset of S1?
Yes,
Yes.
sir.
Okay. This S is called the closure of R. What closure? Reflexive closure. Reflexive closure. Reflexive closure of R. Then how? What should be the definition of the reflexive closure? Reflexive. Sorry.
Sir, R is the subset of S, and S is a subset of S1.
Reflexive closure. So how you define this? You see here. So reflexive closure is a relation. This is also a relation. This is also a relation because it is a set of the Cartesian product of A cross A. Set of the Cartesian product A cross A. So this is also a relation. So reflexive closure of R is uh, is another relation. Reflexive closure R is another relation S such that such that such that S becomes reflexive and S must be subset of subset of any other relation, any other reflexive relation, reflexive relation containing R. This is the basic definitions. Why? You see, R is the any relations. S is called the reflexive closure. Okay, how you construct such that S becomes reflexive. Okay, and this is the part. These four are the construct the relation R. So S is the this is also a reflexive relation. S1 is also a reflexive relations. So R S is called the reflexive closure of R if it is S is reflexive and any other reflexive relations, okay, of this set, any other reflexive relations that contains R. That means this contains also the entries of R, and S must be the subset of this. That means S is the smallest, like this. This is R, this is R, this is your S, this is S1, this is S2, like this. Okay, that means we consider the smallest subset or the smallest set, which all these S1, S2, all are the because we have 2n square. This is the number of relations on a set A. Okay, now among this, R is the any relation, but it is not reflexive. But we consider the another set S, which is reflexive, containing R. That means S consists of all the entries of the R. Okay, and S is the subset of any other relations that contains R, like this. That means S is the smallest. How can we construct the reflexive relations? By simply add the rest of the AA. Suppose we have the matrix A, okay, and we have the relations some R. It is not a reflexive. So how can you make it reflexive? So simply add the terms AA to the R. Okay, that is the lowest set that contains R as well as this. So you see here are what is the lowest subset? We just 3 3. We include only 3 3. So 3 3 3 3. You may include 3 2 also. Okay, but it is not a closure. Closure should be the smallest set or the smallest relation so that it is reflexive and contains the R also. This also is a reflexive, okay, but we have a S such that this S is the subset of this S1, so it is not a closure. This is the closure. Okay, similarly, if you want to make it the symmetric closure, what you will do? It is a symmetric closure. Okay, it is a symmetric, so it is a symmetric matrix. So if you are consider the suppose 1 2 3 is here, okay, and then what happened? Hello, hello,
Yes, sir. Yes.
hello. Okay. I thought so. 1 2 3 and R is a relations. R is a relation like 1 1 2 1 3 1. Okay. So what should be the closure of this? Symmetric closure. Symmetric closure of R. Just define this one. 1 1 should be here.
1
2 1
2.
should be here and 3 1. Okay, so what should be the rest entries? We should enter here so that
2 and 1.
this becomes symmetric. 1 2 is here, so this is 1 2 should be here, and 1 3 should be here. Okay, so this is the closure. Is it? Now you can construct the other also. Suppose 1 1 2 1 3 1. Okay, 1 2 1 3 3 2 2 3, like like this. Okay, but this is also a set that contains the R and it is the reflexive. But what happened here? This is what happened. This S1. This S is the subset of this S1. Okay, so it is not a closure, but this is a closure. That means we have to consider the smallest set such that the property P holds here. Property P means symmetric, and this also contains R also. Okay, important is transitive. So next class we will discuss this one. Important is transitive. So transitive closure, it is not easy to find the transitive closure, and whatever we have the algorithms that is applied for this transitivity. Okay, so Friday from 9 o'clock, everybody are free? Friday?
Yes.
Yes, sir.
Okay, you haven't any class. So Friday, next class on the Friday, tomorrow I'll take class from 9 o'clock. Okay. Today I conclude this one.
Yes.
Any queries related to this topic?
No.
No,
No, sir.
Yes.
Also, can you please mark
Any?
out the difference between the digraph of transitive, not symmetric and anti-symmetric? So I got confused between the two.
You see, you see here diagram. This is symmetry. If we have a opposite edge, if we have a opposite edge, that means suppose this one is absent, this one is also absent, no problem. What is the method of symmetry? Symmetry, that means if A belongs to A is R related to B, implies B must be R related to A. This is the condition for the symmetricity, but not for all, not for all AB. Okay, so if there has a opposite edge, okay, then it is symmetric, otherwise it is not symmetric. You see here, suppose we have a 1 over here, 1 over here, okay, it is 0, leave it, this becomes 0 over here. Okay, then these are the symmetric, that means there has a opposite edge of the vertex or the nodes. If it is not, then we say that it is a anti-symmetric, or you may simply, I'm just considering, you see you have the book of Kenneth Rosen. In that book, you go to the page number 485 and 486. There it is defined over here. You see, it is like a relation is reflexive if and only if there is a loop at every vertex. Okay, and a relation is symmetric if and only if for every edge between the distinct vertices in its diagram there is a edge in the opposite direction also. If for every edge between the distinct vertex in the diagram there is an edge in the opposite direction, leave it. By the way, so if vertex, okay, so each vertex has the edge, and if between each nodes, if we have the opposite edges, these are the edge, okay, these are the edges, then we say that it is symmetric. It is written here, a relation is symmetric if and only if for every edge between the distinct vertex, okay, distinct vertices is its diagram, there is a edge in the opposite direction also. It is the case of the symmetric. It is in the page number 485. Okay, and what is the anti-symmetric? A relation is anti-symmetric if and only if there are never two edges in opposite direction between the two distinct vertices. Is it clear? So
Yes, sir.
you see here, it is a symmetric and it is non-symmetric. It is a symmetric, but it is a non-symmetric. Okay, because we haven't any opposite edge for each node.
Okay, sir.
Distinct. B to B it may happen, but not the distinct. Okay. Any other queries? Any other queries?
No, sir.
Okay. Let me take the attendance. Okay.
Thank you, sir.